main learning objective for this section is to review the proper usage of the InterVista 469 setup program. Topics covered include installation, setup, digital input-output, thermal model, current elements, motor starting, RTD temperature, and voltage elements. SR-469 software configuration. Once installed, the 469 must be configured using either the keypad or PC-based software. In this section, we install the InterVista 469 setup program and configure the relay to protect the motor for a simple cross-the-line start application. This example is intended for teaching purposes. To ensure that the InterVista 469 setup program operates properly, the minimum computer hardware specifications must be met before proceeding with the software installation. Please reference the cover of the CD or the notes if you are downloading the software from our website. The following procedure should be used to install the software. Power up the computer and start the Windows program. Insert the GE Multilin CD into the CD-ROM drive. If the installation program does not start automatically, go to the Windows Start menu and select Run, and using the browser, select the setup.exe file and then press Enter. Once the CD has launched, the user will be presented with a screen that is similar to the GE Multilin web page. Once the software has been installed, a 469 PC software icon will be added to the GE Power Management Program Group. This section will provide an example of programming a relay using the InterVista 469 setup program. The first step in using the setup program is to configure the communications to allow us to talk to the relay. We will do this by selecting the Device Setup button located above the online window on the left side of the screen. In the window that appears, you will see the panel on the left-hand side showing the text, "Please add a site." This indicates that no sites or devices have been set up for communications. First, we need to add the site that will contain the relay. Press the Add Site button found at the top of the window. A new site will be added with the default name, New Site 1. To change the name of the site, click on the Site Name field and type in a new name. Next, we will add all of the devices that we want to be found in that site. Highlight our site by clicking on it and press the Add Device button. Two things should now have occurred. The name of our site would have changed, and a new device will be added to the site with a default name, New Device 1. We now need to configure that newly created device. In the panel on the right, click on the Device Name field. Type in a new name that describes that relay. Open the pull-down menu. Because we are configuring to communicate with an RS-232 serial cable, we will select Serial from the menu. Several new fields will appear in the area below. The Modbus slave address is used to identify specific devices for communicating on the network. When communicating through the front port, there is only one device on the network. Therefore, there is no risk of communicating with the wrong device. For this reason, we can leave the Modbus slave address to the default of 1. In the COM port field, select the communication port of your computer that the serial cable is connected to. The COM port that we are using is COM1. Therefore, we will leave this at the default. The baud rate has been set to 9600. The order code and firmware version can be read from the relay itself to fill in the last two fields. Press the Read Order Code button. Press the OK button. Once the device setup has been completed, you will see the name of the site you have created in the device window. By opening this menu, you will see the name of the device that was set up for communications. Opening this menu further, you will see the menu structure for the relay itself. This is one of two methods that can be used to view the settings and actual values that are present in the relay. By double-clicking on the settings, you will see the available settings for the basic operations of the relay. By double-clicking on a settings menu, you will see the specific settings for that function. The second method for viewing the settings in the relay is to click on the Set Points drop-down menu. This will show a list of all settings pages within the relay. Please note that the grouping under the Setpoint drop-down menu matches the structure of the Setpoint pages found in the relay. If you familiarize yourself with the menu structure by using the PC program or the keypad, the transition to the other interface will be very simple. Customizing the appearance of the setup program can make it easier to navigate the settings of the relay. For instance, the settings windows can be resized. For this training CD, we will be using the drop-down menus located at the top of the window, so we can close or shrink the file and device windows to allow a larger viewing area for the settings. We will now go to the 469 System Setup menu and start to configure the 469 for the application. In the Current Sensing tab, the Phase CT Primary, Motor Full Load Current Rating, Ground Current CT, and Differential Current CTs are set. Phase CT Selection. The correct selection of the motor's phase CTs is critical to ensure proper relay operation. For acceptable resolution, the phase CT's primary rating should be no more than twice the motor's full load current rating and no less than the rated motor full load current. The closer the CT primary rating is to the motor full load current rating, the better the phase current resolution. From the example motor datasheets, we can see that the example's motor's full load current rating was found to be 347.5 amps. The protection engineer then selected standard 400 to 5 CTs for both the phase and ground CTs. Motor full load current setting. From the datasheets, we can see that the motor's full load current rating is 347.5 amps. Therefore, the 469 motor full load current was set to 348 amps. Ground fault detection. There are several options for the ground fault detection depending on the grounding system used and the diameter of the motor cables. Zero Sequence CT. In this application, the Zero Sequence CT was chosen given its advantages over the residual configuration. In Tab 2 of the System Setup, if voltage transformers have been installed on the relay, they must be configured under this tab, in addition to the motor's nameplate voltage. Moving to Tab 3, the nominal power system frequency and phase rotation is entered. From the Set Points menu, the Digital Inputs menu is selected. As a minimum, the starter or breaker status input type must be configured. From the Set Points menu, we then move to the Output Relays menu. As a minimum, the trip relay reset mode and operate time is configured. Note that the trip output can be forced to check the trip circuit operation. We will now move into the protection menus and set up the minimal number of protection elements required by this application. From the Set Points menu, the protection menu is selected and then the Thermal Model submenu. In this application, the motor is equipped with RTDs and its service factor is 1.15. Therefore, the overload will be set to 1.25 or 125%. From the thermal modeling section of this course, we learnt that a formula based on empirical data states that K is equal to 230 divided by the per unit locked rotor current squared. The locked rotor current is equal to 631%. To get the per unit locked rotor current, the locked rotor current of 631% is divided by 100% for a value of 6.3. The K value is now calculated by dividing 230 by 6.3 squared, which equals approximately 6.0. Hot-cold curve ratio. The hot-cold curve ratio is calculated by simply dividing the hot safe stall time by the cold safe stall time, or use the motor thermal limits curve. For this example, both are available. Using the data sheets, the hot-cold curve ratio equals 16 divided by 18, which equals 0.89. Stopped and running cool times. The motor manufacturer's specifications indicates that the motor running cool time is 1 hour 15 minutes, while the stopped cooling time is 2.5 hours. In the thermal modeling section of this course, we learnt that the stopped and running motor cooling time constants can be calculated by dividing the stopped and running cooling times by 5. Therefore, values of 15 and 30 minutes will be used for the running and stopped cool times respectively. RTD bias minimum. Set to 40 degrees Celsius, which is the ambient temperature obtained from the data sheets. RTD bias midpoint, The center point temperature is set to the motor's hot running temperature and is calculated as follows. Temperature rise of stator plus ambient temperature. The temperature rise of the stator is 80 degrees Celsius, Class F rise by resistance, plus 10% hotspot allowance, obtained from the datasheets. Therefore, the RTD center point temperature is set to 90 degrees Celsius plus 40 degrees Celsius, or 130 degrees Celsius. RTD bias maximum. This set point is set to the rating of the insulation or slightly less. A Class F insulation is used in this motor, which is rated at 155 degrees Celsius, and so 155 is entered. Selection of the overload curve. Standard curve number 7 was found to be just below the cold thermal limit and above the hot thermal limit, and therefore the best fitting curve for this application. With the cursor, select the standard curve style and enter a value of 7 for the curve number as shown. At this point, it is appropriate to show how to enter a custom and voltage-dependent curve. Custom overload curve. In the Thermal Model tab of the Motor Thermal Model, the custom curve is selected. The user then programs the drawn curve by entering trip times for the 30 pre-programmed multiples of the pickup level. The final curve can be viewed with the C-curve selection. Voltage-dependent overload curve. The voltage-dependent overload curve is constructed in the following way for the motor thermal damage curve shown. Construct a custom curve for the running overload thermal limit, as was done for the custom curve. If the curve does not extend to the acceleration thermal limits, extend it such that the curve intersects the acceleration thermal limit curves. Enter the per unit current value for the acceleration overload curve intersect with the custom curve for 80% line voltage. Also enter the per unit current and safe stall protection time for 80% line voltage. Enter the per unit current value for the acceleration overload curve intersect with the custom curve for 100% line voltage. Also enter the per unit current and safe stall protection time for 100% line voltage. The 469 takes the information provided and creates protection curves for any voltage between the minimum and 100%. For values above the voltage in question, the 469 extrapolates the safe stall protection curve to 110% voltage. This current level is calculated by taking the locked rotor current at 100% voltage and multiplying by 1.10. For trip times above the 110% current level, the trip time of 110% will be used. These figures illustrate the resultant overload protection curves for 80% and 100% line voltage respectively. For voltages in between, the SR-469 will shift the acceleration curve linearly and constantly based on measured line voltage during a motor start. In our application, standard curve number 7 was found to be the best fitting curve for this application. So ensure that the standard curve style is selected and a value of 7 has been entered for the curve number as shown. From the Protection menu, select the Current Elements menu and then the Short Circuit tab. The Short Circuit Trip. The short circuit trip should be set above the maximum locked rotor current, but below the short circuit current of the fuses. To calculate the setting for the short circuit pickup, perform the following steps. Calculate the maximum locked rotor current by multiplying the motor's full load current of 347.5 amps by 631% for a result of 2,192.725 amps. This result is then multiplied by 1.7 to raise the short circuit pickup just above the maximum theoretical asymmetrical starting current to a value of 3,727 amps. Within the 469, the short circuit trip pickup is set in units of the phase CT primary rating, which is 400 amps. Dividing 3,727 by 400 gives us a result of 9.31. Therefore, 9.31 is entered as the short circuit trip pickup level. Unbalanced alarm and trip. This feature is primarily used as a means of detecting the loss of one of the motor's phases. If there is little or no voltage unbalance, a setting of 10% for the unbalance alarm with a delay of 10 seconds, and a trip setting of 25% with a delay of 5 seconds is appropriate. Ground fault. In our example, we are using a zero-sequence CT. The zero-sequence CT is checked to ensure that it wouldn't saturate under maximum ground fault conditions. Refer to the CT selection portion of the course for detail on the CT saturation calculations. The trip is set to latched. Owing to the noise immunity of the zero-sequence configuration, the ground fault trip level will initially be set to 0.25 CT, which is the most sensitive setting possible. Phase differential. Phase differential protection may be considered the first line of protection for phase-to-phase or phase-to-ground faults. Unfortunately, this motor does not allow access to both sides of the field windings. Therefore, this element will be left disabled. If access to both sides of the field windings was possible, then either the core balance or summation differential configuration could be used. If the core balance differential configuration was used, the starting and running trip pickup level would initially be set as sensitive as possible due to its inherent sensitivity and noise immunity. If, on the other hand, the summation configuration is the pickup level, it will be set less sensitive than that of the core balanced configuration owing to CT error. The flux balancing configuration, 3 CTs, will still be set more sensitive than the 6 CT summing configuration due to the additional CT error. Ensure that the phase differential trip has been set to off. We now proceed to the motor starting menu. The acceleration trip setting. In our case, across-the-line starting is used. A setting of 13 seconds would be appropriate. Jogging block. With this option enabled, the number of starts per hour and the time between starts can be set as per the datasheet. This may be considered backup protection to the thermal model. For our example motor, this information has not been given, and so the option should be left disabled. Enable Start Inhibit. This feature can only be enabled after 5 consecutive starts and if the load is consistent for each start. The restart block feature may be used to ensure that a certain amount of time passes between stopping a motor and restarting that motor. If, for example, a motor is driving a very high inertia load, once the supply to the motor is disconnected, the rotor may continue to turn for a long period of time as it decelerates. For a short period of time, the motor becomes a generator, and applying supply voltage out of phase may result in a catastrophic failure. The restart block feature is strictly a timer. The 469 does not sense rotor rotation. In our example, we have no additional information regarding restrictions on a restart, and so this feature can be left disabled. RTD temperature. If, as in the case of this motor, RTDs are being used, they must be configured in the RTD temperature menu. Stator RTDs. RTD trip level should be set at or below the maximum temperature rating of the insulation. This example has a Class F insulation, which has a temperature rating of 155 degrees Celsius. Therefore, the stator RTD trip level should be set to between 140 degrees Celsius to 155 degrees Celsius, with 155 degrees being maximum. The RTD alarm level should be set such that it provides a warning that the motor temperature is rising. For this example, 135 degrees Celsius would be appropriate, since this motor is designed for a Class B rise. 130 degrees Celsius is its normal hot operating temperature. Trip voting has been added for extra reliability in the event of RTD malfunction. If enabled, a second user-selectable RTD must also exceed the trip temperature of the RTD being checked before a trip will be issued. If the RTD is chosen to vote with itself, the voting feature is disabled. Each RTD name may be changed if desired. Bearing RTDs. The bearing RTD alarm and trip settings will be determined by evaluating the temperature specification from the bearing manufacturer. If VTs have been installed, the under and over voltage alarm and trip elements can be configured. Under and over voltage protection. The under voltage trip should be set to 90% of nameplate unless otherwise stated on the datasheets. The over voltage element should be set to 110% of the motor's nameplate unless otherwise stated in the datasheets. Actual Values menu. The Actual Values menu provides measured values in addition to powerful maintenance fault analysis tools such as the event log and the Waveform Capture. The 469 Waveform Capture allows the user to capture 3 phase current and voltage waveforms under pre-configured conditions. To set up the 469 Waveform Capture, perform the following steps. From the 469 Setup menu, select Preferences, then refer to the Trace Memory Trigger position. This determines the position of the trigger for waveform capture. The number programmed represents the percentage of cycles that will be captured and recorded in the trace memory buffer prior to the trigger or trip. Let's set this to 10%. Trace memory buffers. This determines the number of traces that will be captured and the number of cycles for each of the 10 waveforms captured. Note, 10 waveforms are captured for each trace showing all currents and voltages. Let's set this to 8 traces by 14 cycles. To review captured waveforms, go to the Actual Values menu and select Waveform Capture. The 469 Event Log. To review the event record, go to the Actual Values menu and select Event Record. Event 01 is the most recent event, and Event 40 is the oldest event. Each new event bumps the other event records up 1 until Event 40 is reached.